part 2 of this first example here. I had a office hours, so I had to speak with my graduate assistant, so I had to chop this thing in half. Here's the example where we were taking this and we're designing it, right? So we have the rectangle designed. We ended up deciding that it was going to be 1.5 wide by 0.5 wide by 1.5 high. We decided to use 1030 annealed steel. So let's continue this and do the circular part right here. Well, we already have the material. It wouldn't make sense to use a different material. And I always hate when the thing shows through on the other side. So let me flip that over. There you go. And let's see. Okay, so now we need to do the get the loads that are going to be taking place like right here. Okay. The view, we really need two. We need the other two views, right? We need to be looking. Do we need that? No. Let me think. No. Okay. What we need to do is to find the torque that's going to be onto this. Like this force is going to create a torque around on this cross section, and this force is also going to create a bending moment that's going to be about the y-axis as it's drawn right here. So it's good to make these headings, right? Circular section, right? So this is the circular section design portion of the design right here, and we want to make an FBD. And don't get lazy with these, right? Because when you get lazy, it's easy to then like make mistakes, right? To run across places where errors are going to concern. So once again, we're looking at the same thing as we did right here, but now I've drawn in the little circle right there because that's the moment. It's actually going to have the same value, to tell you the truth, but that's it's good not to be lazy, because I've found when I've overlooked things, like I didn't bother with the free body diagram, that's where something was different about it that I just didn't recognize. But by way of drawing the diagram, I'm able to pick up where possible mistakes took place. So this is going to be the reaction, and actually this is going to be at B in the y direction. And I think I forgot to label that over here. So let me say this was at A in the y direction, right? Right here is at B in the y direction, and right here is the reaction moment, but this reaction moment is actually the torque that's being placed onto this section, because this thing is right here, it's twisting, so we're drawing it for right there. So there's some of the moments about the x-axis once again. And once again, this is a simple problem, but we need simple problems as part of the examples so that we can get progressively more difficult problems. So here it is, counterclockwise is the torque, and 250, and then once again this is 12 inches from there to there. So the torque is equal to 3,000 inch-pounds. Now we also want to get what the bending moment is going to be, and I think I decided, oh, by the way, we should always do this right here. This is YZ right in here, and this is also YZ. Yeah, this is also YZ. And now I want to look at it. I think I'm going to look at it from this direction right there. I didn't on mine. I actually looked at it from over here. I'm gonna do it from over on this side right there, because that's how I have it written on mine right now. And so from that side over there, what we're really looking at right here is this right there, right? So FBD, we're declaring that it's an FBD, and if I'm looking at it that way right here, this is the X direction and this is the Z direction. recognize that's the x direction, z is up. We're looking from that direction, so that x goes to the right over there. And this load is now right there, 250 pounds. So we're going to have, once again, this is going to be RB. I said Y right there. It's a crazy thing they made Z as the thing, so that's actually Z. Good practice, and that was not no, that was about X. That was correct right there. Okay, and this was Z. So right in here we have a moment reaction, and that moment is about the Y, and it is at B, I guess, in the about the Y-axis. So that's the location of the thing. And let's see, that one's going clockwise. So this one must be going counterclockwise. We have that right? Yes. And this distance now is going to be 8, right? And we're really kind of making, we're saying it's to the center of this piece right there. So we don't have to worry about the little small sizes of the thing. So this is about the y-axis, and here you go counterclockwise as for the page, and so we just say that it's MBY minus 250 times 8, and so MBY is equal to 2,000 inch pounds right there, right? So so this is going to cause bending, and this is going to cause torque, right? So there's no, we could draw the other view onto this, but there's, just because of the arrangement of this thing, right? If there was a force coming out this direction right in there, or a force coming in that direction right in there, we'd have to make sure that we're drawing the other views so that we could get the total amount of moment that's being placed on the thing, and then we would take so we would have the bending moment about the Z as well, right? But right now it's only about the y-axis. The thing is, so the stress that we're going to have as part of this, right? So okay, so we're going to use von Mises stress, which you'll recall is going to be sigma squared plus 3 tau squared, and the square root of those two things together. So let's write out MC over I squared plus 3 times TR over J squared. And because it's a circular cross section, we have a little bit of something easier. We can go M, and this is going to be D over 2 pi over 64 d fourthed squared plus 3 tau d over 2, right, instead of the r, pi over 32 d fourthed squared. And then there's probably an example somewhere in the book where they go ahead and write this out in this way. I think I need to look. So you could go ahead, if you are watching this, you could go ahead and tell me that, so I can share it with the rest of the class, right? So that's your assignment here. So you see that we could pull some things out. We have that there's 16 here, so there's 16 times 2 right there, pi and d cubed, and this is squared, but then we take a square root of it, so we could do this algebra right here. And by the way, we're going to set this thing to the allowable. So the allowable is still 23 KSI, but what we're going to do is, I guess I wrote this right here, allow equals, and I went 16 pi d cubed, right? And I said times the square root. Now this is 32. This is going to be 2 inside that square, so it's going to be 4 times m squared plus 3 times t squared. Yes. And now I want to solve for that diameter. And we know it's going to be the cube root and 16 pi over sigma allow, right? Because we could take that d cubed, put them over here, divide out by there, and then square root of 4m squared plus 3t squared cube root. So now we have an equation for this situation. Maybe we want to use that again sometime, or put it into a spreadsheet or something along those lines when we're trying things out, just to make it useful to ourselves so we don't have to do it every time. We put this in here, and I decide to not play around with my units at all, and just use the full 23,000 right in there. This is 2,000 in bending. This is 3,000 inch-pounds in torque, all raised to the 1/3, and I get a diameter of 1.132 inches right there. Okay, so 1 1/4 isn't enough. 1 and change, 1 1 1/8 is not enough. 1.125 is not enough, but 1 1/4 would be enough. But remember, we made this one 1 1/2 tall right there, right? So that's 1 1/2 tall. So maybe it makes sense to make it 1 1/2, even though it's going to be over designed. It's going to make it more sense. So we'll say D is 1.5 inches. So now what we've done is we've picked a material, and we've designed the rectangular part and the circular part. Perhaps what we want to do now is make a drawing that shows all of these things, so we can present it to whoever's going to build the thing, or that's going to be our so quite often our deliverable will be some type of sketch, and we can look at the thing, and probably want to have and we'll ghost that in there, and we will say that this is our 1.5 inches. This right here is our 0.5 inches. This, I guess I will put this right here as 1.5 inches diameter. We still need these other dimensions, where this is 8 inches to there, and I could have put this underneath there, so this is 12 inches right in there, right? And so voila, and then write out AISI 1030 annealed steel. And I think steel is spelled with 2 E's. I don't know. I know. Okay, so there you go. We're an engineer. Now we're a design engineer. We just designed something using ME470 stuff. I'm going to do another example where we do fatigue. But here we go. I wonder how much time that took. Let's see how much time that it took. That was another 13 minutes of your life. Great.